Swayam Prabha. Digital India. Educated India.
Hello, I welcome you all to the first class of this course, High Performance Computing for Scientists and Engineers, and this is the first module which we are discussing, Fundamentals of Parallel Computing, and as I said, this is the first lecture which is Introduction to High Performance Computing. While welcoming you all to this class, we need to see what are the focus of this course and who are the target audience for the students and application engineers who belong to that group for which this particular course is designed. Of course, I will say it is not the exclusive group whom I intend to attend this class. There can be students and professionals from different areas who are also welcome in this class. So, high performance computing is a very important topic in today's computational science as well as engineering, because in second decade of 21st century, this is third decade of 21st century, we really try to understand many complex physical phenomena, many complex biological systems, many complex social behaviors. We talk about data driven sciences, we talk about very accurate and high fidelity physical simulations which require high computational infrastructure. Because we try to understand the problems with much rigor, the computational complexities increase, and simple computers or a single computer with probably the fastest processor and largest RAM is not sufficient to handle that complexity. And we also discuss about supercomputers today, and most of the real engineering designs as well as most of the involved scientific computations as well as many other computer application problems in many different fields like biomedicals, like economics, like sociology, like public health are solved using these supercomputers. And that is why today there is a need that application engineers, scientists and other domain experts should be able to work in the supercomputing platform. In most of the cases, they will deploy some of the software which are already developed to port in that supercomputing platform. However, they need certain understanding of the platform itself as well as the methodologies that this high performance computing or supercomputing technique is using. We can see, and I will discuss it later also, that our government, the government of India has launched National Supercomputing Mission few years ago in a view to promote supercomputing and train manpower who are who can have jobs in maintaining supercomputers and also in porting different applications into supercomputers. This is one side, that we need application engineers, application scientists, domain experts who are using high performance computing facility. The other end is that as these applications are being demanding day by day, therefore we need a pool of computer engineers, computer scientists and computer application specialists who can help the domain scientists to work in the supercomputing platform. So, there is a need both from the computer scientists, computer engineers perspective as well as from the perspective of application scientists and domain experts to step into supercomputing with a view that they understand each other's requirement, that the computer scientist or computer engineer understands the requirement of a domain expert, as well as the scientist can communicate his requirement, the domain scientist or the design engineer can communicate his requirement to the computers engineers community. And unfortunately, the courses in high performance computing are mostly looking into computer engineering perspective. However, people from science and engineering domain many times fail to jump into these courses simply because of the fact they are not trained for that, they do not have the right prerequisites. And therefore, a gap is created in which computer engineers talk in a different language, and while they are looking into networking, the algorithmic point of view, the hardware point of view of supercomputing, the application of supercomputing which is in parallel computation is scarcely looked upon by them, which is required by the application engineers. And as we are looking for going into next decades computing with exaflops computing, we are setting up many petaflops supercomputers all across the country, there will be a need to bridge that gap. Therefore, this particular course, I myself is not from a computer science background. However, I have been using supercomputing facilities for nearly 2 decades, and I am also teaching courses which look upon applying high performance computing or supercomputing techniques with the most cutting edge techniques like GPU computing into scientific problems. Hence, the goal which I set in this course is to bridge the gap. That is, we will discuss about high performance computing technique, we will discuss about the computer science as well as mathematics part involved in the high performance computing applications. However, we will keep a focus that our goal is to look into scientific problems or engineering problems. Well, let me jump into the class. And another important thing is that because we as a country we have a mandate to develop manpower trained in supercomputing. So, in this class probably teachers or aspirant teachers who want to pursue a career in teaching computational science and scientific computing probably can get some benefits, while they can use some of the materials being discussed in this class to train the next batch of students. Well, let us start the discussion for today's class. The first as a first class we will first discuss what is serial computing and what is parallel computing in a supercomputer or in a high performance computing architecture. We typically take a large job, distribute into many small jobs and ask many computers to work in parallel to solve that job. So, what is that? As an abstraction, how that can be represented. Then from a scientific computing perspective, what is the requirement of large scale computing? And I am a computational fluid dynamist by training. So, I will take a computational fluid dynamics example and see that in certain cases to understand the right fluid mechanics, we need supercomputing or large scale computing. With a simple sequential computer, we cannot even finish the job in any time scale. Then we will look into some high performance computing architecture. We will see what are the elementary steps in parallel program, because parallel programs are the pointer which will refer several times, and it is what we are trying to do over this course. We are trying to see how can we write parallel programs and make them efficiently work over different high performance computing infrastructure using several APIs. We will look into it later in this class. So, the first module of this course will probably discuss mostly on the fundamentals of high performance computing, but in the subsequent modules we will discuss how to write parallel programs for different platforms. And then what I have been discussing over last few minutes, that what is the structure of the course, I will try to discuss that in a more structured manner, that what are we going to discuss in the course and what will be the books for that. Well, so let us see what is serial computing or our standard sequential standalone computers computing, and how does it compare with parallel computing. As we can see from the figure, we talk about solving a puzzle, and this puzzle is a simple puzzle like putting 4 pieces of a Lego kit together and building a block. So, if 2000 pieces are given to a person and he is a tedious monotonous job, but he can finish that in probably 10 hours, that taking 4 of the pieces from this 2000 which matches in, say, in certain sense in color or orientation, and putting them together to make a single puzzle. Now, a person wasting 10 hours for this has certain implications. So, let us ask another person. So, the previous guy was wearing orange shirt. Now, I ask another person who is wearing a grey shirt to join hands with him, and we will also take few of these puzzles, and concurrently they will work on the same problem. So, 1000 puzzle each it will go, and we will see that they are solving this, all the puzzles are combined, and this is finished in 5 hours 30 minutes. That means each one is solving 1000 puzzles each. So, if one can do 2000 in 10 hours, why two are taking more time? Of course, we can estimate the fact that they are wasting some time in chatting among themselves, but let us see that is not the case. We are using robots for doing that, who can keep on doing this monotonous job without having human wastage of time, human nature of time wastage. So, still it is 5 or 30 minutes, because some time will be wasted, or some time has to be spent while stacking 1000 puzzles each. From 2000 puzzle, one has to take 1000, another has to take 1000. This will take some time, and some time will be gone for again putting all the solved puzzles together, or all the Lego blocks together, which will adding up, it will take close to 30 minutes, and there is need of some synchronization in between them. So, question is, why not in 5 hours? There is a question, because best we could have done it in 5 hours. So, we have to waste some time while working in parallel, in compare to the fact that if we can perfectly divide a job into divide the serial job or sequential job into multiple computers. So, instead of running one do loop here, we are asking two of these to run two different do loops. However, it is taking some more time, and we need to see can we reduce this time and solve it in close to 5 hours, or if not, what else can we do. So, that is one of the goal while we will look into look through this class, especially in the first half of this course, when we will discuss fundamentals of parallel computing. We will see what are the overheads when we asks multiple computers to work in parallel, like solving the puzzle. Many people are coming and solving the puzzle together, distributing the number of pieces among themselves. So, the overall time requirement can be reduced. However, there is some overhead, it is not reduced exactly by the number of people dividing the total time for a single person by the number of people. So, there is some overhead, how to do and handle the overhead. Well, so now see, why is it required? Well, we understand that it will cut down some time, but the fact is that if you run multiple computers, it require capital investment in terms of purchasing the computers, operational cost in terms of running the computers. So, instead of running, it is not a person, it is not a man power which we are using computer powers. Instead of doing it 10 hours or 5 hours 30 minutes in two computers, we could have done it in single computer. Some time you have to wait, does it matter? So, let us look into that, and I told you that I will give an example from my field of work. So, we take a fluid mechanics problem, that a high speed flame in premixed combustion is propagating through a chamber, through a cubic enclosure. So, this is an enclosure with 1 meter by 1 meter by 1 meter in size, say, and a flame during combustion is propagating through it, and this is typically a turbulent flow problem. So, for turbulent flow problems, these problems are governed by a parameter called Reynolds number, which is given as RE, and RE is equal to density into velocity, or let me write it in some other location, velocity into diameter, or the length of the, or width of the channel, divided by viscosity. viscosity. So, if we see that for Reynolds number, the grid spacing to resolve the smallest turbulent scale. So, we solve it using a computational fluid dynamics process. So, we can see that this problem is a function of all the parameters, velocity, temperature, not temperature, velocity, pressure, everything is some way a function of Reynolds number. Now, if we try to use some computational to solve it, we can see that the grid spacing, sorry, okay, why this is not happening. Well, the distance between 2 points while resolving this flow is called the grid spacing. For turbulent flow, to resolve the smallest scale of turbulence, it will be Reynolds number to the power minus 3 by 4, and that tells us that for Reynolds number 10 to the power 6, which is the Reynolds number we typically handle for high speed some of the high speed combustion problems, in a cubic geometry there will be 10 to the power 13 grid points required. And so, solution over 10 to the power 13 grid point with our best possible algorithm for fluid mechanics problem, for one time step, one set of solution, it will take 10 to the power 13 floating point operations. Well, typically a time step is 10 to the power minus 3 seconds. So, solving for 10 seconds will require 10 to the power 4 time steps, or 10 to the power 13 into 4, 10 to the power 17 floating point operations. I assume I have a computer with 10 gigaflop per second. I do not have it, but let us assume I have a computer with 10 gigaflop per second. So, what is the total time requirement to solve this problem? 10 to the power 17 flop divided by 10 gigaflops, which is 10 to the power 10 seconds, or 317 years. So, just solving in a 1 cube geometry of a turbulent flame propagation, which is much more simple case than an actual industrial problem. If we try to resolve the smallest scale of turbulence, we take 317 years. So, what do? Typically, we do not resolve the smallest scale of turbulence lengths at even today's date. But if we try to do something close to that, we have to wait for 317 years. I need a computer which will operate over 317 years, and I need a legacy of my students who will be living, or whose students, his student, somebody who will be living after 307 years, and they will see that what one of the person 317 years back started running, what is the results of the job, and probably it will of no use that time. I mean, our science will progress in a direction where we might not be interested to know this. I mean, forget that this is not doable, this is not feasible, that a problem can be solved in 317 years. But let us still assume that we have some superhuman setup to wait for 317 years to see what happens in a 1 cube combustion flame for 10 seconds. Still, we can see that the matrix size which will come out for solving this will have at least 10 to the power 13 rows in the matrix. The minimum number of size of the matrix will be 10 to the power 13 into 16 byte. It is much more than any of the available RAM size. We cannot load the matrix to a computer and solve the problem. So, we forget waiting for 317 years, it cannot be solved even for a single iteration, even we cannot load this problem into the computer in a RAM of the computer. And therefore, if we try to solve a large scale scientific computing like turbulent flow, there can be many other examples. Molecular dynamics can be one example, protein simulations can be examples, cloud simulations can be examples, a plethora of black hole simulations can be examples, a plethora of examples can be given where a single computer cannot handle this job. So, we have to think of something different, and that is where we tell that we need high performance computing. Right now we thought of computational science, which is domain science, is shaking hand with mathematics, and they are using some computer methods, simple things like C or Fortran or Python program to get their job done, and this is called scientific computing. Now we brought the third guy in, who is computer science. So, mathematics plus domain science, which is scientific computing. Now they have to distribute the scientific computing job into among many computers, and these computers have to communicate, these computers have to synchronize and solve a problem completely in totality. So, this is parallel computing, where these scientific computing jobs are broken down into many small jobs and given to many of the computers. So, this is parallel processing plus scientific computing, which we are discussing in this course, is basically high performance scientific computing. Well, let us go to next slide. So, what is the basic idea? That I have a large job, its RAM size is large, is a variables with gigabyte, megabyte, more than variables with gigabyte, more than 100 gigabyte, more than terabyte memory, and one computer is asked to solve it. So, it is typically a serial, sequential or standalone computing. We will use these terms again and again. So, one computer solving a problem. If it is a large problem, it is like one person has to lift a very heavy load and work with that. If it is extremely heavy, he may not be able to lift the load. So, that can be the first difficulty. The load or the memory can be too large, so that one computer cannot load it, or it will give you memory allocation issue, whatever way you try. The other one is that if the computer still can take the load, it will take astronomically long time. Astronomically long time is 317 years, 4 cycles of Halley's comet is there. It is an astronomical time. So, so the solution becomes parallel computing, that is, ask many people to carry the load. A large piece of memory is used and many computers are together working for the same problem on the large memory. It needs much synchronization among themselves. So, if they have to work with the large load, they have to work together. The other way is that break the load into multiple small blocks and ask different computers to work on that. And there are small memory units, but there is a requirement of more communication, because they are having different pieces of the same load. They have to know where each others are going. The left one is known as a shared memory load, and the right one is known as, distributed memory. Right one is known as distributed memory. These are the two paradigms in parallel computing. We can distribute the main problem, the memory of the main problem, into several computers as small memory units, and ask all the computers to take care of a small memory unit and work into it, which is a distributed memory. Or we can take every entire memory in a single RAM, or the way a single RAM works, in a single motherboard many pieces of RAMs are given, and it practically behaves as a contiguous memory, and ask many computers to work on different areas of this memory. So, whatever the way we do it, and we will discuss about shared memory and distributed memory in much detail in a week or so. So, whatever way we do, it requires distribution, that the job, including memory part or without considering the memory part, it has to be distributed among many computers. There is a requirement of synchronization among the work of the computers, and there is a requirement of communication. And these are the components, this distribution, synchronization and communication, these are the components which gives me overheads. Sorry, let me change it. These are the components which gives me overheads. For this part, what is doable in 1 hour by one computer in 10 hours, 4 computers cannot do that in 2.5 hours. There is some overhead. So, overall they take more time. So, the elementary steps of in parallel programming will be how many people are doing the work, what is the degree of parallelism, that is what we call degree of parallelism. In many cases we can see, say there are 5, there is a block which can be divided only into 5 5 pieces, maximum 5 people can work on that. There is a matrix which has 100 rows, maximum 100 computers can, if we have to add 2 matrices with 100 rows each, maximum 100 computers can be asked that they will work on each of the row, or maximum we can have 10 to the power 4 computers that they will work each of the elements. We cannot use more computers than that. So, how many people are doing that work, that depends on what is the maximum number of decompositions or distributions possible on the main work. Also, what is the maximum number of computers available to me, what is my resource limitation. If I have 10 computers, I am working in 1000 by 1000 matrix, I cannot distribute into 100 jobs, that there will be some sequentiality in each computer, it can be distributed into 10 computers only. So, that is degree of parallelism. What is needed to begin the work? Some initialization is needed, so that the people who are working together on a problem, or the computers which are working in the single problem, they know that they are working in this problem, and these are the initial data needed to everybody, so that they can in parallel or concurrently work on the problem. Who does work? The work has to be distributed. Access to work part, which data which one requires and what will be the IO by each computer, whether they need info from each other to finish their own job, whether there is a requirement of communication on fly while doing their own work, or maybe sometime it is required after their job is finished, they need to send some data to some other computer, because final work cannot be done without that. This is communication, and when they are all done, it has to be synchronized. And then the results have to be collated. So, 4 pieces of code going 4 rooms will not be of sense if you are shifting a code from one room to other. So, there is some requirement of synchronization, and finally, all the pieces of code, all the stands of the code, the main bed has to be put together to get your own code. So, what is required to collate the results, that is the next thing. And for doing all these things, we can see that distributing jobs into many computers, initializing them, communication, synchronization, a simple C program cannot handle this. So, we need APIs, which are message passing interface, MPI, OpenMP, Open Multiprocessing, CUDA, these are the APIs, and precisely these 3 APIs, how to use this to make a parallel program, we will look through this particular course. Well, so one question is that if we can increase number of computers, will it be better? And say I can divide a job into 10 to the power 4 small concurrent jobs. If I use 10 to the power 4 computers, will it be better? And we will again look into it in much detail in subsequent classes. So, that will say that if we increase number of people for carrying a load, it will increase speed, as a sense less weight for each people. However, there can be non-uniform distribution, somebody is getting heavier parts, somebody is getting lesser parts. So, someone is sitting idle, whether someone is slowing down the process because he has much more weight. There is requirement of communication and synchronization, and there will be idle time for some of them, and therefore, which will add to latency or overhead. So, as we are increasing number of computers, we will see we are getting better speed, in a sense that the time requirement is reducing. However, this latency is also increasing, and we will see that as we increase number of computers, the speed or number of operations we are getting per second is not following a 45-degree slope. There is some overhead where the actual speed is reducing with increase of number of computers, actual speed up is reducing, and there will be certain stage where it will be flattened down. We should not use more computers after that. But what is again the question is, how many computers, how many processors we can use concurrently to solve a process, what is the optimum number? And this is something where an application scientist have to make a call, that yes, it gives better speed up if you increase number of computers, but we can see that the line is flattening down. So, should we still increase using more computers, or should we say that we will not use more further computers, but and solve with this number of computers? It is still not decreasing, still increasing, but the slope is reducing. So, what will be my optimum number? That is one of the issue, and we will look into these things I am telling you in detail. So, now these are solved in HPC clusters, high performance computing clusters, and while discussing the previous point, it is important that we discuss this also. And this is one of the fastest supercomputer here, which is many computers stacked in a rack, and many racks are connected via interconnect switch. You can go to the to one of the controlling computers and ask them to distribute the job among many computers and work together. And again this architecture will look into detail, but from hardware point of view, these supercomputers are known as energy sink. They absorb huge amount of energy because running computers require a lot of energy. As they run, they warm up and the processors gets warmed up, and you need cooling to keep the processors functioning. So, huge thermal load is requirement. And one important parameter is power usage effectiveness, or PUE, for any supercomputing center or data center. We typically call the houses which host these supercomputers as data centers. So, right, data center. So, the one of the parameter in seeing what is the energy requirement of a data center is PUE, which is total energy requirement divided by energy requirement by the IT or computing and networks unit. So, which the total energy is the IT part energy plus thermal energy, lighting energy, other losses, etc. So, it is seen for most of the supercomputers this number is close to 1.5. That means, if 1 unit of energy is spent for running the computers and networks, 0.5 unit is spent for AC and thermal load and other relevant loads. So, if we run a computer, we are not spending money or energy in terms of the electricity to run the computer, but we are also spending energy in terms of air conditioning and other loads. Therefore, running multiple computers is also very expensive, which is another parameter while deciding how many computers should we run, that what is the energy requirement of the computing job. And supercomputing is not very energy friendly, that is why nowadays we talk about green computing, energy friendly supercomputing, etc. Well, one of the ways of green computing is GPUs, where graphics processing units or GPU, which are preliminary designed for game development, but later, so these are many small computing units with relatively okay type of memory and very small cache connected in a board, and these are used as graphics cards in many computers, but they are also developed as general purpose graphics processing units or GPUs and shown to have good performance in scientific computing. And it is seen that over last few years, last 2 decades, GPUs give much more speed than CPUs, and they require much small amount of energy also. In a small, instead of building a large, having a large building with many computers, ACs, etc., a small computer, a small workstation with a GPU card. GPU cards are costly than computers, usual computers. With a GPU card, you can get good performance. So, these are one of the ways of having green computing. However, because GPUs have very small cache and very rudimentary processor architecture, the computing in GPU requires some special attentions. Very simply, we cannot do GPU computing in terms of memory management as well as in terms of decomposing the jobs. Special attention and special training is required. So, they are known as very good performance with relatively small energy and space utilization. Now, if we look into the leading supercomputers, it is important. You can look into top500.org, which publishes the top 500 supercomputers. We can see the fastest supercomputer gives 200,000 teraflops per second speed, and it has 2 million CPUs, 2 million cores into it, and of course, there are few GPUs. So, there are first few supercomputers, and they are mostly from United States and China and Switzerland. China and United States have very good presence in top 500 list. India is not doing very well, not in the top of top 500 list. The 57 and 100 computer in top 500 list are from India, and these are Indian supercomputers which have whose speed is falling much behind than the leading supercomputers. And in order to promote supercomputing in India, I talked about National Supercomputing Mission, or NSM, has been launched by Government of India, which looks into several aspects like setting up high performance computing infrastructure, training manpower, promoting science which involves supercomputing, etc. And we hope to improve our ranking in top 500 supercomputers. So, some of the examples, one example is computational biochemistry, where vesicle fusion study, how lipids are propagating into the cell vesicles, that has been studied. It is seen that 4 million, 4 into 10 to the power 6 particles are required for one vesicle and solvent, and LAMPS molecular dynamics software is used over 30 million CPU hours in Cray XT5 supercomputer. And this supercomputer was earlier it was in top 500 list, but it is now decommissioned in 2019. It has 224 into 224 256 cores, and the peak performance was 1.75 petaflops. So, we will again and now we will discuss about flops, which is one measure of how good our supercomputing is, which is the flops is given by floating point operations per second. How many floating point operations the supercomputer can do in a second, that is the flop speed. And earlier we saw that the turbulent flow calculation, it was taking 10 to the power 7 second, 17 flops. So, if we can have multi petaflop system, 10 to the power 9 flop floating point operation per second, or even more than that, we can, instead of 317 years, we can probably think it solving in a year or in less than a year. So, this is important, that how many operations can be done in a second. This is a measure of performance of supercomputers. The next one is a black hole simulation, and it is also seen with different uses of that MPI or a OpenMP, the API I talked about, communicating across the processors and increasing the number of processors. The time requirement from 0.1 microsecond per grid point comes down to 0.04 microsecond per grid point. So, there are different uses of parallelization and different uses of hybridization of these APIs, which can give better speed. The next one is a cloud simulation using scientific computing. Here we can see that the time is in different computers is a function of how vectorizing is again parallelizing the solver, how the solver is parallelizing, and with right parallelization of the solver, what was a Jacobi 2D was taking 45 seconds, similarly a vectorized Jacobi 2D takes 17 seconds, we can bring it down. And this computation is done in GPUs, but it was a much primitive GPU in sometime in 2003 this computing is done. Now GPUs are much faster, and one of the point he is writing that our optimization have not taken much advantage of usage of textures as lookup tables. While fragment programs provide computational flexibility, it comes a cost. Lookup tables are important as they are important in CPU computation, but that time the lookup tables were not being optimized for GPUs. Also, the linear solver is Jacobi, because even 2003 the advanced linear solvers were not ported for GPUs. Now these are done and you can get much better speed. So, one of the forecast this group was making, Harris in 2003, has come true, that GPUs have made certain development and the computing speeds have increased. This is in from our group, a computational chemical engineering problem in chemical industry, how liquids mix and what are the mixing times, etc. It took 2 months computing time in 1000 processors over 3.8 million iterations, and we can see that what is the ideal speed up and how actual speed up varied. Some computation using biomedicals flow in a stenotic artery in GPUs, and we can see compared to multi-processors, multi-CPUs or single CPU, the graphics processing unit or P100 GPU has give almost 70 times better speed than a single processor and 10-15 times better speed than 32 core GPUs. So, CPUs. So, as GPU is much faster than multi CPUs also, which came through biomedical computations. Sorry. Now, one of the important part, after we have shown some of the examples, the course structure, I said it is designed for potential HPC users as well as developers with various background. It requires some understanding of computer programming, some understanding of preliminary understanding of computers and its architecture, though no computer science course is prerequisite, as well as no scientific computing course is also prerequisite. Whenever required, I will try to give you the preliminaries of these parts. The 4 modules are fundamentals of parallel computing, which will include parallel computer architecture, performance metrics, memory management, algorithm design, etc. Then we will see for shared memory applications how OpenMP based programmings work, for distributed and also for some of the shared memory cases how message passing interface or MPI programming works, and for GPU we will look into CUDA. These are few books. One of the textbook will follow Grama Gupta Karipis Kumar Introduction to Parallel Computing, then Parallel Programming using C and OpenMP by Michael Quinn, then the canonical book on MPI by William Gropp from MIT Press. For CUDA, we will look into CUDA programming guide developed by NVIDIA both in C, and PGI CUDA, which also look into Fortran, and Shane Cook's CUDA programming guide. And Livermore National Lab has a good website for HPC. You can go into this website and get a lot of tutorials out of it. So, as a conclusion, we have developed some concept of parallel computing. So, some idea we got about what is high performance computing, parallel computing. Some the elementary steps of parallelizations are discussed, but we will discuss in much detail about the design of parallel algorithms and how given one particular problem we can decompose it into multiple problems which can be solved concurrently in parallel computers. Some important HPC systems like GPUs, HPC clusters, and some of the leading supercomputers are shown, and some examples based on HPC computations are shown. So, well, we finish the first introductory lecture and we will start working on the later part of the course. Especially we will take the module on fundamentals of parallel computing, including architecture, the memory management, and the parallel computer architectures, and we will see then what are the metrics to understand whether a parallel computing program is performing well or not in subsequent lectures, and then we will go to MPI, OpenMP, etc. Thank you.